So I'm Marcus. I'm going to talk about state-space thermal control of CubeSats. So the topics will be, I'll give an introduction on what controls is. Then I'll do a little to talk about thermal modeling, and then I'll do a quick example of some of my research, which is feedback control. So to start, what is a linear state-space system? So typically what you do is you'll have some mathematical model that typically involves ordinary differential equations that describes your system. These are of order n. And what you can do is you can take these order n ODE and then write it as the messing up.
It keeps flashing black, yeah. Also just gonna sit closer so I can read the equations.
Working fine now. So typically you have an order n system, and then you can write that nth order system as n first order ODEs. And so to do that, example would be like F equals MA. So your ODE would be y double dot equals 1 over MF. And then your state variables, you would just say y equals x1. And then y dot equals x2 and y double dot equals x2 dot. Should I just leave it as, maybe it's the presenter view?
We'll see.
Okay, I'll leave it as this and see what happens.
No, it's not that. You might as well be in presenter view.
It's the HDMI connection, it's flaking out.
Yeah, I would just try. You have a different HDMI port?
I'm not even using it, I'm just connecting to the TV.
Like an AirPlay?
No,
It's a room computer.
Yeah, it's a room computer.
Oh, so it's just the TV, okay.
Yeah.
Maybe try HDMI to the TV instead.
Let's see, just it's fine right now.
Okay. Well, it's more
I guess it's a connection issue, so I just.
okay. The Zoom is probably fine, yeah.
Yeah, the Zoom's fine.
Okay, should I start over? I'll go back it.
Yeah.
So, yeah, the topics for this, just starting over, well, I'll talk about, some basics on linear control theory. And then I'll go through some thermal modeling, and then I'll give a quick example of thermal controls for spacecraft. So to start, a linear system, typically you have a mathematical model that is an ODE that describes your system. Those ODEs are like nth order, and you can write your nth order ODE as a system of first order ODE. So an example of that would be F equals MA. If you write your ODE in this form with y double dot equals 1 over MF, where F is your input into the system, you can have these state variables where you write y equals x1, y dot equals x1 dot, which is actually x2, and then y double dot equals x2. So you're just going through saying each state is a derivative of the other state. And then you can represent that as a system of equations represented here. So this would be your linear system. And then the general form is, x dot equals ax plus bu. And so A is typically called the state matrix or the dynamics matrix because it contains all the dynamics of your system. So if you look at this system right here, the A matrix is 0, 1, 0, 0, where the 1 corresponds to x2 and x2 is y dot. So it's your velocity. So it maintains the properties of your system. And then B is called your input matrix because that's how your inputs enter into your system. If we then convert this into a discrete system, basically it's the same thing except you use you use a derivative approximation and then substitute that in and work through it. And you get a very similar form. Where everything, for all practical purposes, they're all defined the same. Except now that your system depends on how fast you sample your system. If you then look at what this system has as a stability, if we just assume no input, so we go back to the general form, it's x equals ax plus bu. We assume that b is 0. We'll get the system as x, t plus 1 equals ax. If we then step through time, just go through each individual step and notice the form, it's x of k equals a to the k, x 0. So as k goes to infinity, then the x of k will go to 0 only if the eigenvalues of a are less than 1. They have a magnitude less than 1. So, and those eigenvalues are called poles. So if we go back to this system here, we can look at this system, we can look at the A matrix, and when we look at the eigenvalues, then we can immediately tell whether our system is stable or unstable based off of the eigenvalues. So that's stability. And then if we look at controllability, is defined as the initial state, so x naught, can be moved to any final state in a finite amount of time through an input u. So clearly, it's basically if I have a matrix vector, if I start at 0, can I move that vector anywhere in the state space in finite time? And a test for that is called the controllability test, where you form this controllability matrix. And it depends on B and A, because B is your input matrix, A is your dynamics. And so a relationship between the two obviously is important. And so if the rank of your controllability matrix is the size of A is n, then basically you can control any state to any other state in finite time. So if you can do this through the input u, what should the input u actually be to control the state to where I want it to be? And this is called state feedback control laws. So if we choose u to be of the form r minus kx, where r is your reference signal, k is the gain matrix, and x is your state, you can have the open loop system. And then if I just plug in this control law into my open loop system, I get this new system, which is a minus bk x plus br. If you look at the two systems, the open loop one, you have your regular dynamics. So you have your regular eigenvalues, which could be stable or unstable. If your system's controllable, then I can use this control law to alter the eigenvalues of my system through the gain matrix K. So it's really important. This is how I can change the dynamics. I can change how my system physically responds to inputs through this gain matrix K. And the gain matrix K is up for the designer to choose. And picking K specifically is called pole placement. Essentially, pole placement is you have your characteristic equation for your eigenvalues, and you just match it to specific poles you want. So for example, this is just a quick graph where you had a system, it was at 0 state, so it's all its states were initially 0. And then I implemented this control law, and I was able to alter the gains to then track and follow the reference signal. But you can see that it doesn't follow to 1. There's a little bit error. That's called steady state error. And essentially that steady state error is due to a scaling issue with your input. So if we modify this control law to now include G, which is a scaling term, we can eliminate steady state error. And that just basically affects the input B. So you still have the same system, A minus BK, and then plus BG. So again, you have your open loop dynamics, which is just defined by the eigenvalues of A. Then you have your closed loop dynamics, which is defined by the eigenvalues of A minus BK. And you can use K to change those eigenvalues. For steady state tracking, you've added this G term, and essentially this is the formula for G, but it comes from the final value theorem for state space systems. So that's essentially the background, a quick background on controls. And then to do some thermal modeling for heat transfer. Your heat transfer equations depend on time values and spatial values. So if I'm gonna write it as a discrete system, I have to evaluate it at discrete times and spaces. So that the temporal values are pretty easy because you can just write that as t plus 1 minus t divided by delta t. But then to evaluate it at spatial values, you have to create a mesh. And so if I create this mesh in the top right, where the white dots are the nodes, the orange is the control volume, and then we look at the conductive heat transfer from every node to node 1, we can create this energy balance. And you assume that all your energy is positive into the node. In doing so, you arrive at this equation. So this is rho CV delta T dt, or dt dt. And then you have conduction from 2 to 1, 3 to 1, 4 to 1, and so on. You can write this conduction value as K AX dt dx, and then approximate that derivative as T2 minus T1 over delta X. And you sub these all into your equation, and you arrive at the bottom one for node 1. And if you repeat this analysis for each node, you'll arrive at a system of equations for every node. And you'll see here that you have T1 to the T plus 1, which is, if I look at my discrete time system, you have the same thing. So your states in this thermal model will actually just be the temperature of your system. Yeah, and again, you just do that for each one, and then essentially to solve this finite difference equation, you just step through time. But now we have to consider radiation as well. So for radiation, you form an enclosure, and you assume that it's diffuse in gray, that the radiation is diffuse in gray. And you also assume that each surface inside your enclosure is of uniform temperature. And basically, this is just skipping a lot of math. You arrive at this system, the top equation there, and for each surface, you have an equation, and then you can solve that system of equations for Q, which is your heat flux. And that basically tells you that Q right there is the instantaneous net radiation loss from that surface. So if we go back to this one for the thermal modeling, just included conduction, but if we go in, we can include radiation into that finite difference equation, which would just be subtracting Q. The reason why you subtract it has to do with overlapping control volumes. We defined conduction to be positive into the node, but here in these drawings, it assumes a boundary, a control volume of Q going in, which is actually leaving that control volume in the other one, so you have to subtract it. And so that's pretty much all the background for thermal controls and or controls and then thermal modeling. But if we looked at a problem to emphasize what's actually capable here, if we assume we have an optics box, which is the orange, and inside the CubeSat structure, which is the blue. If it's initially at 300 Kelvin, it loses heat radiatively to the surroundings, how do you develop a controller to control the optics box at 305 Kelvin with no steady state error? So to do this, you would model the structure as a thin shell. Basically, it just means it has no energy storage. And then you would model the optics box as a system of 8 nodes. And then so for each node, you would define there would be a control volume, and that control volume would have this equation where it's the energy storage equals energy in plus the energy generated. And so energy storage is your rho CV dt dt, and then your energy in is your conduction minus your radiation. And then your Q gen is what the input would be. So if you had a heater on that surface, that would be modeled as internal heat generation. So the pseudocode for this would be, you have an initial temperature, you go through, you solve your system of radiation equations for Q, which is your instantaneous net radiation loss. You then substitute that Q into your finite difference equation for temperature. And then you just step through that over and over and over again, and you get a temperature profile, which here you can see that this is the temperature profile of that CubeSat. And then I compared it with Thermal Desktop just as like a validation method, and it matches really well. So the next thing would be That however, radiation depends on, if we go back to the radiation equation, it depends on T to the fourth, which is nonlinear, which poses an issue for linear state space control. So what you have to do to avoid this is you have to linearize your radiation term. And to do that, you just take a first order Taylor series approximation, substitute it in, and redo all your calculations. And so there you can see the blue dashed line is your linear approximation, and it's pretty good for the first, 1 times 10 to the 4 seconds. Which is okay, because your control system is going to be updating probably faster than that. And so in that region, you have a pretty good model. This, however, when you do your Taylor series, you get a constant term from that. And so instead of being A or X dot equals AX plus BU, it's X dot equals AX plus BU plus some constant term, which is not the correct form. So to handle this, you form an uncontrollable system where you originally have, you have all your controllable states here, and then you have an uncontrollable state there, which is the constant term. So if we look at it, the AC, the controllable states, is going to be A, X1 through 8 on both. So it's an 8x8. That's your controllable system. And then the bottom last entry at position 9,9, that's your uncontrollable state, which comes from the constant term because you can't control a constant term. And then your A12 is just a vector of ones in the last column. And so if you represent it that way, it has open loop. This matrix, big matrix A, has open loop eigenvalues that are all less than or equal to 1, which makes sense because it's thermal modeling and it's heat transfer, which goes to an equilibrium point. So it makes sense that our system is stable. If I then go and add the control law, GR minus KX, if I add that control law, my system becomes this, where now I have the choice of choosing 2 gain values. I can choose K1, K2, or 3 gain values, and then G. So you can choose K1 to, there's a MATLAB command called place, which basically is a numerical algorithm that places the poles where I tell it to place them. And so if I tell them to place the poles here at 0.12 up to 0.8, I will actually change the eigenvalues on the system. So you see here, this is my original system, and you look at the diagonal, they're all the eigenvalues that I told them to be. So I chose how the system is going to respond. And then you pick K2 to basically just cancel out the dynamics. So you're essentially saying, I want this equation here to be 0, and just solve the, AX equals B. And then again, you choose your G to be in this form, as this will ensure that you have steady state tracking. So this result looks like this. So if I give my reference signal as a step function, I've now controlled my system to go from 300 Kelvin to 305 Kelvin. And the reason why you get this slow response between is because I've chose my eigenvalues to be steps. So if I went back and I chose them all to be at 0.1, then all the temperature profile will be the exact same for every state. And again, each state here is the temperature of each node. You can go in and then do some funky things with different pole placements, but basically pole placement matters because if you look at the right figure, you have values like 0.99, which is really close to 1, which is becoming unstable, which leads to a really slow response. But if I place my pole, say closer to 1 or closer to 0, I get a really quick response in my system. But a quicker response means you need to have a higher input. And so for that reason, you can't just place all your poles at 0. If you place all your poles at 0, then you'd have an infinite input. You'll require an infinite input to get you to those states. So that's kind of a drawback of linear control, is that, we talked about controllability, which is going from an initial state to a final state in a finite amount of time. So that finite amount of time just can't be infinite. It could be really large. It just can't be infinite. So if I choose 0, then my input is going to be huge and will do it, but it's not actually a feasible input response for your system. So you have to choose. And then And another interesting thing is that these, if you have a pole placement on the real axis, it's called a first order system. If I then go and place a pole off the real axis in the imaginary plane, you get a second order system, and that's why you see these overshoots. So there's different ways you can, there's a lot of theory in how to do pole placement to give desired responses. But essentially, this is how you would control your CubeSat to 305 Kelvin. To reiterate, the big key points are that you have your A matrix, which is your dynamics matrix, which has eigenvalues, which tell you whether your system is stable or not. And then if your system is controllable, you can find an input gain matrix, K, to alter those eigenvalues to give you a desired response. So you could theoretically have an uncontrollable system to start with that goes off, just does whatever. As long as it's controllable, you can find an input that will drive the system to what you want it to be. And that's pretty much state-based control for CubeSats. That's all I have.
In your in your conduction finite difference bed, if you have do you have like a full mesh or do you have elements, and how do you handle just like empty space there from like?
What do you mean empty space?
Like, so for example, if you have an enclosure in your CubeSat, the space between that empty, it's not conducting, so you just define you only conduct within like your CubeSat, or is the whole space of mesh, or?
Yeah, so I just have here's the mesh. So this is the CubeSat. It consists 8 nodes for the orange. And then I modeled the enclosure as 1 node. I only consider conduction between, so the way you would model is you have conduction between the orange bit, and then you're solving the radiation equations between those two.
Okay.
So the outside of this orange is a surface, and then the CubeSat structure is another surface. So when you go to this radiation modeling, you have just surfaces that all have an area, a temperature, and a flux associated with them, and you can solve this system of equations. And that's how the two surfaces talk to each other.
So in that final example with the CubeSat, so what you're showing here, when you're controlling all of these nodes, is so this represents like if you were able to control the temperature of like all of those nodes that you were showing. So like, yeah, you had like several different heaters like placed on
on each. So it's AX equals BU. So U is your input, which would be the heater that you attach to it. So that's what this Q generation term is. The Q generation term bottom, that's modeling the heater, and that's attached to each node.
Okay.
And then so each node has an input on it, and then since each node has an input on it, I can control each state or each temperature. And then I have, you write it in the correct form, and you can derive this control law that will drive it to that temperature, basically. Yeah, and then there's other theories. This is kind of like a quick overview, but you can do like optimal control where you solve. It's called LQR, where you're fitting you basically solve an optimization problem, and you can find the most optimal Q for a cost function, or most optimal U, the input, for a cost function. And so there's other theories on top of that. You can do like state estimation. So like, for example, if you didn't have an output, so you couldn't read the temperature. So if you had 9 nodes, you would have a center node that you obviously can't attach a thermometer to and measure the temperature of that, but you could estimate the state from other information in your system and still use feedback on an estimated state. But yeah. Did that answer your question?
Yeah.
Question?
Yeah, you're thinking about how to doing the location of error. I mean that if your instrument have some tolerance range, did you do any estimation on that?
If the system had, if there was noise in the system?
I mean the tolerance, like if you want the temperature between 100 to 120 Kelvin, And how did you estimate? So your target point probably was 111 or something like that. And how did you estimate the system error?
Estimate a system error.
Yeah,
Did you assume the steady state error was zero? I think she was like
Oh.
being asked what happens if you turn that into a range and basically get like a dead band? Like how do you
Control within a
control within
that
a range
yeah.
range.
instead of a single value you're trying to hit?
Because in reality, there's no way you can fix that thing.
Well, you can use Kalman filtering where so it's actually not a bad. I'm not sure how you would fix it within a range because in steady state error, you're basically assuming. It's called final value theorem where you assume that you're tracking your reference input, and when you track it, you get the equation for G. But if you had noise in your system, or like if you had noise and you would say like, okay, because I have this noise, I can't actually control it to this value, but I want to control it between these values. That's not an issue because Kalman filtering is like a Gaussian. It's statistical modeling where you're estimating your state statistically, and you would have a really accurate model of where you were.
Does everybody know what Kalman filtering is? Familiar with Kalman filtering?
I've heard the term thrown around before, but I don't.
I know
actually
people use it for pairwise probing actually.
Yeah, it gets used all over the place.
Yeah.
Yeah, I mean, it's so. I don't know. It's if you were to, you would alter your control law basically. If you go back to these control laws, if you look up like a Leuenberger observer, that's the non-statistical Kalman filter. But basically you estimate the state from your outputs. So you have output inputs. And so you would add another, I guess I can write it. I don't know this off the top of my head, but it's of the form where you add like an other gain L, and then you have your Y, and you subtract the estimate of your state. And then you add this into control. So it's A X plus B U plus this. And you have your actual output, and then you have your estimated output, and you're subtracting the two. But if you did a Kalman filter, instead of this L, you would have K, which is your Kalman filter gain, which is like you use it's a Gaussian estimation of what you have your output data, and you assume some statistical properties of that output, and then you use that to inform how to feedback this and minimize this error between the two.
Is this Kalman filter KALMAN?
Yes.
Yeah.
Oh.
Yeah. So if you like, yeah, so I guess your question is like, do I need to have that band? Like, I don't think you need to have a band because you would just use Kalman filtering and control directly to that.
My question is about, so in realistic, there's no way your control system is perfect. So there will always be a how to say, the errors in your target. So actually, like you want to control at 111, but the temperature will look somehow like this.
Basically,
But you're controlling it. So I'm using
Yeah.
output, I'm using state feedback. So
Yes, I understand there's a feedback, but could you give the estimation of the error of the target?
what's your
Like
jitter
how
around your
much
target
it would
temperature?
bounce around.
Yeah.
Yeah.
Oh,
Around
I'm
your
not sure.
target. Yeah.
Which
I'm not
would be
sure.
from like.
Well, if you assume a first order system, you don't have any jitter. It just goes to it because it's
No,
first
no,
order.
that's theoretically, right? But like if you have
No,
a
if you-
real control system, there's gonna have
Yeah.
electronic noise, your sensor's gonna have noise. That kind of thing.
Yeah, I'm not sure. So, but yeah,
Probably not a lot, but
Probably just like low pass filter.
Yeah, time average.
yeah, but that's what the Kalman filter is.
That's what I call it.
That's what it
Kalman
is.
filter is just smoothing. Like basically it's doing something intelligent with a batch of data and coming up with a better result, whether it's time averaging, like it's
Yeah.
But the question about if you how do you estimate performance if you think about like, because you're gonna, depending on your filter, depending on what it is, right, you're gonna overshoot, you're gonna overdamp, you're gonna do other different things, and how do you like
How do you plug
Do
in
you-
noise into simulations of this type? of
Yeah, a
stuff?
little bit, like, yeah, how do you actually evaluate how well your loop is gonna do without actually doing?
Well,
Other than just getting yourself.
in pole placement, there's some theory where you're placing in the complex plane and certain pole placements. If you choose a pole placement, that characterizes overshoot, response time, settling time. There's all those things that you can design for. So if I had my system, I say, oh, I want it to respond in 10 seconds. I want it to have an overshoot of less than 2%. You can, then there's formulas to calculate what the pole should be to enforce that. So that's kind of like performance characteristics, I guess. I don't know if that's to the degree that you like, but
Also had a question about your enclosure boundary. You said it's cooling to vacuum, like radiatively. I assume that was a CMB, I'm sure. Yeah. Do you also have solar heating as a boundary condition? Like,
no, I did not model like like a solar flux, but you could do that. It's pretty
That's
simple. You
really
just
difficulty to do that.
huh?
no, you just add another
I think it
term.
would be a boundary condition term.
You just add in here for each node. You just add
Yeah.
because it would just be in the in term. It would just be constant if you assumed it was constant or something like that.
And it'll depend on your material too. If it's aluminum, it should
Yeah.
equilibrate pretty quickly.
So,
It uses you-
yeah. So the one thing I didn't show in this was that technically you have this system of equations. And you actually need one more equation, which comes from the control volume of your enclosure. So you have your inside, you have your optics box, and that's communicating with the structure radiatively. But then the structure itself is communicating with deep space radiatively.
Yeah.
So this analysis here, if I assume the inside, I need another equation to account for radiation loss to the environment.
Yeah.
And you would just do a control volume again of this form of, that's why I said it was a thin shell, because there's no energy storage. So it'd be 0 equals En. And your energy in would be energy loss to deep space, but then also a flux in from solar radiation.
Yeah, that would be cool if you could do that, mainly because that would be a time varying term. And that I don't know how it would affect your control. I think it's just looks
For
fine.
this
And it'll
controls,
just change your times, yeah.
you have AX plus BU,
Uh-huh.
which is, you assume that A, B, C, and D are constant values. So if you had a time, that would add in a time varying, which is a lot, I don't know anything, it's a lot harder.
Yeah.
I don't know anything about that.
I think you can still do it with this, and it's also, I think it's implicitly stable. Your solutions don't blow up if your inputs are like reasonable.
Yeah, unless you like run out of power.
Yeah.
Right, yeah, so a lot of simulations they run for solar highs and solar lows,
Yeah.
and they just do them as steady states, that kind of tells you how much juice you.
Oh, okay. Yeah.
But yeah, so like. Interesting question that will apply to anyone building instruments is, what does an ICD look like in an instrument? And what does a thermal ICD look like?
I don't, what's an ICD?
What's an ICD?
Uh-oh.
I gotta go, man, lucky for you guys. As an interface control document. So if you have, if you're bringing your instrument to the spacecraft, how do you, you have to do a thermal design for your instrument, but it depends on all these surroundings and all these things. So how do you come up with the documents or a document or whatever it is, that allows you to go do your thermal design with being able to incorporate whatever all these inputs are for those models.
Mhm.
And that's what's always really hard, because no one ever knows the answers.
Yeah.
But yeah, figuring out every single term is those things that's what goes into an interface. So you're gonna have all your conduction terms. So if your instrument's attached to some metal bulkhead or whatever, right, you're gonna have a conduction term for each one. And you're gonna have your radiation boundary. And each wall, all gonna be a different temperature.
Yeah.
And so that's all super key for coming up with like your thermal control. So there's a spacecraft design, which is basically like the spacecraft thermal model. Like you have your spacecraft, that's your outer shell, and you have your sun, that's where you deal with that. But that's only like a high level one. And then they kind of have some detail come up with the boundaries, and then they give them to the instrument designer. figure that out from there, and that determines all your boundary conditions. So that those are called like your interface control documents, which provides your parameter space where you go and build a thermal system. And it's really hard to tell actually, because of the detail. It starts off really easy, and then as like the design matures.
Is that only for like thermal stuff or is it also electrical?
Everything. So and you often have mechanical ICDs, thermal ICDs, electrical ICDs, software ICDs. Often they call it an ICD and then it's like everything in one giant computer document. But yeah, that's kind of that's the game of how you learn to work together and build things in large groups. It's figuring out the terms that matter. And you'll get most of them right. No, sorry, I gotta run. Thanks, this was really interesting. Yeah.
So is any problem from the room? If not, I will gonna to end the room. Thank you everyone for there.
Very good.